Okay, so in this activity, we are going to look at the difference between simple interest and compound interest. Okay, there are two different ways that interest can be accumulated. So suppose that your family deposits $10,000 in an interest-bearing account for your college fund that earns simple interest each year. Okay, so this is you. Your friend's family deposits $10,000 in an interest-bearing account for their child's college fund that earns compound interest. So here's you, here's your friend. Okay, so we've got our years over here as our input. Raise your hand and tell me what you are noticing between these two tables. Tyler?
The right side is increasing more.
Okay, the right side looks like it is increasing more. So they both jump up by 400 at first, but then what happens? Yeah, this one goes up more than 400. Okay, what else do you notice, Addison? What do you notice about this column? Very good. Everybody write this down. Do you notice that this is linear growth? This is linear growth because we have what's called a common difference. Many of us struggled with this idea on the test, the difference between a common difference and a common ratio. So let's go over here. Does anybody recall how do you figure out the common ratio? Xander? Very good. Everybody grab your calculators and start doing that. And then do it for the next line down, 10,816 divided by 10,400. And if you notice, are you getting 1.04? Okay, so let's write this in. We are multiplying by 1.04. This page, by the way, is going to become your notes in your notebook for this. So make sure you are adding all these little details, even if it might be really clear to you. So when we multiply every time, this is called a common ratio, and that's what makes it exponential. Okay? All right, let's go down here, and we are just going to sketch a graph of this. We're not going to be super particular, so let's draw a little break symbol because we're just going to have this go up here to 10,000 as our y-intercept. Why did I put this little break here? What is this representing? Okay, that little break means I'm understanding that I'm leaving out a huge chunk of the graph, that if this is 0 to 10,000, I'm excluding things there. So now I can go 10,400, 10,800, 11,200. I can have these go by 400s. $60, I can't add. 11,200. So this would be 12,000. Okay, so if we start doing this after 1 year, 2 years, 3 years, 4 years, 5 years, this is just going up by 400 every time. That's reinforcing to us that simple interest is the same as linear growth. Okay. Now before, give me a thumbs up if your graph's ready to go. Okay, finish that up. before we move on, what percent is 400 of 10,000? What percent is this? What percent? Yes. 4%. So this is 4% growth, but since it's compounding simple interest, we are adding 4% growth based off only the initial investment. Okay, so before we go on down here, we're going to write an equation for simple interest, S of x. So looking at that line you drew, what's the y-intercept? Okay, so the y-intercept is 10,000. And what is our slope? What do we add every time? 400. So there's our simple interest equation. Okay. All right, let's take a look at compound. So I'm going to do another little break here. Compound interest starts at 10,000. After the first year, we're exactly the same. We're at 10,400. But after the second year, we are a little bit more than one box up. The third year, we're a little bit more than another box up. And it's hard to see this growth, but we're going to just sketch something like this so you can get an idea of what's going to happen with exponential growth. I'm not worried about you getting all of the y intervals shown, but you just need to see that it's going to start curving upward. We good? Okay, start to write your compound growth equation. Gary, what do you think the compound growth equation is going to look like?
10,000 times 1.04 to the power of x.
Very good. Once again, where do we get the 1 from? Because it's increasing. Good. Where do we get the 0.04 from? It is 4% compounded every year. That means it's like that snowball effect. Okay? All right, now let's go to Desmos because we're going to see a better picture of that. And we are going to put in both equations and we're going to see exactly what happens. Okay, so we're going to rip out page 525, and this is going to go into your notebook as an overview of simple and compound interest. Okay, now we're on page 528. And we're going to continue to apply simple and compound interest growth and decay, but this time we're going to be looking at a population. Okay, so I'm going to give you guys a chance to talk in your groups and kind of do this together, but here's the concept. At this moment, the population of downtown is 20,000, and the population of uptown is 6,000. But over many years, people have been moving away from downtown at a rate of 1.5% every year. At the same time, uptown's population has been growing at a rate of 1.8% each year. So we're going to do this activity collaboratively. So within your table groups, you guys are going to answer these 3 questions as I come around and check, and then I'll ask you to move on as it's appropriate. But I'm going to get you started in the first part. In this scenario, what do you think the independent and the dependent quantities are going to stand for? What's the independent going to be? What's the input? Time. And how are we measuring time? In years. Good job. What's our dependent going to be? Population. And how are we measuring population? As people. Okay? Okay, so for downtown, we want to start our y-intercept up high. And to show decreasing, this is all we need to show. We're not particular yet about points. So downtown is the one that's decreasing. Uptown is increasing. Okay, from what we know about exponentials, is downtown ever going to hit 0? No, because we have what is called an asymptote. Please add this to your book. An asymptote is a horizontal line that the graph gets really, really close to but never hits. And in this case, it's going to be y equals 0. Okay. All right, for the uptown equation, we're starting much lower. So let's go down here. And that y-intercept is at 6,000. And it's going to be increasing. Now, did this population ever hit 0 way back here before time? No, didn't it have to start with something? To start multiplying by a factor, it had to start with at least one person, so it has the same thing. Okay, they gave us these equations, but do you guys agree that this equation is not in the form of y equals a times b to the x power? Okay, so that's what we're going to explore over here. So can you simplify both of these equations so they look like y equals some number times another number to the x power? What'd you say? 20,000 times what? But downtown, isn't it 1 minus 0.015? So we have to figure that out. What is 1 minus 0.015, Xander?
0.9.
You guys agree?
Yeah.
Oops, and this should be t. Good. What's uptown going to be, Avery?
6,000 times 1.018 to t power.
Very good. So what does the a value in each of these situations represent, Bella? What's the a value? Oh, the y-intercept, but in the problem situation, what does it represent? Starting population. Very good. It's our starting population. That's what it means in terms of the problem situation. But in the context of the graph, it's our y-intercept. What does the b value mean in the context of the problem situation? What'd you say? Very good. The b value is the percent of the population. It's their percent of growth or their percent of decay. Okay? All right. If you turn the page, at the very bottom of the page, this is what we've already gone over in a note sheet. Exponential growth is any function that looks like y equals a times 1 plus some growth factor r to the x power. And exponential decay is a times 1 minus r to the x power. Okay? So to finish this up, at your groups, take each of these functions and write them under which scenario they match with. Okay, so check your work here on page 531. out of these choices, these match up here. Now, it is correct that this form, if we do, if we subtract these, it is correct that this equation would also work. But since this one down here is not a choice up here, this is the form we're talking about. Okay, so now you can put either this page and any of these pages into your notebook as assistance for exponential growth and decay. And now you're going to finish up today's assignment by doing the checkpoint that's posted in Classroom.